Welcome to section 4.3. Let me remind you of what we're doing. We're solving second order, linear, homogeneous, meaning equal 0, DEs with constant coefficients, meaning the coefficients A, B, and C are constants. They're not variables. Last time we saw that we could solve these equations by writing down the characteristic equation, which uses the coefficients of the derivatives of y as the coefficients of the powers of r, solving that characteristic equation and looking at the roots. And what we did last time was we did the case where we had two distinct real roots, r1 and r2, and we wrote down the general solution, and we'll do a review of that today, and a repeat real root, in which case we take e to the rt as one solution and then t e to the rt as our second solution. Today, we're going to look at the case where we have complex roots that look like r equal alpha plus I beta. In that case, our general solution is C1 e to the alpha t cos beta t plus C2 e to the alpha t sine beta t. And that's because our fundamental set is e to the alpha t cosine beta t, e to the alpha t sine beta t. And I'll explain where that's coming from at the end of the lecture. It's a little mysterious, and it might seem awkward at first, but after you do a few problems, you'll just get used to writing that down. You do have to memorize this. So let's just jump in and see what we need to know. You don't have to know a lot about complex numbers to do this. You need to know two things. One, what is I? I is the square root of -1. Two, complex numbers solutions will come in pairs, and they'll always look like alpha plus I beta, or alpha plus beta I. Some people like to put the I after the beta. It doesn't really matter. So let me show you how this works. Suppose we want to solve the quadratic equation r squared plus 2r plus 2 equals 0. So we try and factor it. We don't get much luck, so we go ahead and we use the quadratic formula, which I've written down for your convenience. All right, so in this case, we're going to get r equals b is 2, so -2 plus or minus the square root of b squared, that's 4, minus 4ac. 4 times 2 is 8, over 2a. A is 1, so this is over 2. So that's -2 plus or minus the square root of -4 over 2. Now, -4 is 4 times -1. So it's the square root of -1 times the square root of 4. So that's 2i, because the square root of 4 is 2, and the square root of -1 is I. So this is -2 plus or minus 2i over 2. And finally, divide each of these by 2 to get -1 plus or minus I. So our alpha is -1 and our beta is 1. That's all you need to know to solve these problems. You need to know alpha and beta and how to simplify a square root. Okay, so let's jump in and do some differential equations. Okay, so we're going to write down the general solution, and in each case, we're going to state the characteristic equation. We're going to factor it if we can. If it's complex, we won't factor it. And if the roots are complex, we're going to state alpha and beta. So the characteristic equation for this first one is r squared plus r minus 2 equals 0. That factors pretty easily as r plus 2, r minus 1 equals 0. So our roots are 1 and -2. So we're starting out with a review of what we did last time. So in this case, our general solution, this is the easiest case, y equals c1 e to the t plus c2 e to the -2t. And again, the order doesn't matter. You could write c1 e to the -2t plus c2 e to the t. Doesn't matter. Next one characteristic equation is r squared minus 4r plus 4 equals 0. That factors as r, let's see, minus 2 quantity squared equals 0. So that's a repeat root of 2. So I'll just write 2 twice. And so in this case, my general solution, this is the second case, c1 e to the 2t, and then I multiply by t, c2 t e to the 2t. Okay, next one's going to be complex. Write down the characteristic equation, r squared plus 4r plus 7 equals 0. Try and factor that for about a nanosecond and realize you can't, so we're going to bust out the quadratic formula. R is negative 4 plus or minus the square root of b squared, which is 16, minus 4ac, which is 28, over 2a. In this case, 2a is just 2. So that's negative 4 plus or minus the square root of negative 12 over 2, which is minus 4 plus or minus 12 is 4 times 3. Square root of 4 is 2. So that's 2 root 3 times I, because the square root of negative 1 is I, all over 2. And now I'm going to distribute that 2 to both fractions. This is negative 2 plus or minus root 3 I. Okay, so alpha is negative 2 and beta is root 3. That's all we need to know. And then I'm going to plug in to that formula on the first page. So some people factor their e to the alpha t out since it's in both terms. I like to distribute it. So I have one solution and then another. I like to write it like that. Okay, so that's what I'm going to do. So y equals c1 e to the negative 2t, that's e to the alpha t, cosine of beta t. Beta is root 3, so root 3 times t, plus c2 e to the negative 2t sine root 3t. So it looks scary, but it's super easy to find. Okay, next one, characteristic equation is r squared plus 16 equals 0. It does not factor as r plus 4r minus 4. Remember, a squared plus b squared does not factor. It's prime. A squared minus b squared factors as a minus b, a plus b. So this is r squared equals negative 16. Take the square root of both sides. When you take the square root of both sides, you take plus or minus. So r is plus or minus the square root of negative 16, which is 4i. So in this case, solving a characteristic equation that looks like that is super easy. Plus or minus 4i. So alpha is 0 and beta is 4. That's all you need to know. And then we plug in. Y equals c1 e to the 0t is 1, so I'm not going to write down e to the 0t. Just skip that and go straight to cosine of beta t, which is 4t, and then c2, again, e to the 0t sine 4t. Okay, so that's an example of undamped motion. That solution is just going to oscillate forever. Next one's a little different. Write down a DE whose solution is this. Okay, and so to help you do that, I'm going to do this in steps. What are the roots of the characteristic equation? That's step 1. what is the characteristic equation? That's step 2. Once we know the characteristic equation, we can write down the DE. So let's start with the roots. If the solution looks like this, we know that alpha is 0 and beta is 3. Look at the example above, C1 cos 4t, C2 sine 4t. That came from 0 plus or minus 4i. So here our roots are 0 plus or minus 3i. That's 2 roots. Okay, so the characteristic equation, again, just looking at the last example, must be r squared plus 9 equals 0, because r is plus or minus the square root of negative 9. Okay, and finally, once we have that, we can write down the DE. That's y, so the r squared corresponds to y double prime. There's no y prime term, and the 9 corresponds to plus 9y, and that equals 0. So there's our DE. So do it in steps like that. You've got to practice one, part D, write down the DE whose solution is this. So I suggest you start with the roots and then write down the characteristic equation. I'll get you started here. The C1 and the C2t, that's a repeat root of 0, right? Because you would go C1 e to the 0t plus C2t e to the 0t, which is C1 plus C2t. So you have a repeat root of 0, and then these guys, this is saying you have a repeat root of 8. So you have 2 zeros and 2 8s. So the characteristic equation must be, to get a repeat root of 0, that would be r squared. And to get a repeat root of 8, you'd have r minus 8 quantity squared. So there's your characteristic equation. Then to get the DE, you're going to have to multiply all that out to find the coefficients of r. So I'll let you finish it, but that's a start. Okay, so back to, where are we? Okay, we're at the last problem. Here we've got a cubic. Our characteristic equation will be cubic. So r cubed, here's our characteristic equation, minus 5r squared plus 6r plus 12 equals 0. Now there's 4 terms. Whenever there's 4 terms, I try factoring by grouping. But I can see that's not going to work here, because I can pull a 6 out of the first 2 terms. I can pull an r squared out of these. It's just not going to work. So I go with my, let me find a root, so hopefully I can divide and then factor this. So the possible roots have to divide 12. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So there's a lot of them. Start with the smallest ones. So r equal 1, get 1 minus 5 plus 6 plus 12. That's 14, not 0, so that's a no. So let's try the next smallest one, which would be negative 1. We get negative 1 minus 5 minus 6 plus 12. Yes, that equals 0. So if negative 1 is a root, r minus negative 1, which is r plus 1, is a factor. So keep in mind that r equals negative 1 is a root. That's a pun. We'll factor that in later, but we'll consider that later. But right now, what we need to do is take our original characteristic equation right here, this polynomial, and divide by r plus 1. So r plus 1 goes into, that looks like a square root, but it's division, r cubed minus 5r squared plus 6r plus 12. All right, so let's We're going to multiply by r squared, r cubed plus r squared, subtract to get negative 6r squared and bring down the 6r. And now this goes in minus 6r times. And so we get negative 6r squared minus 6r, subtract to get positive 12r and bring down a 12. This goes in positive 12 times. 12r plus 12, remainder is 0. So our characteristic equation now looks like r plus 1 times r squared minus 6r plus 12 equals 0. We know one root is negative 1. Now we need to find the roots of this guy. So we look at it and we say, does it factor? No, it doesn't. Bust out the quadratic equation. So the quadratic equation for this guy is r equals negative b. B is negative 6, so that's 6 plus or minus the square root of b squared, which is 36, minus 4ac, 4 times 12 is 48, over 2a, which is over 2. So that's 6 plus or minus the square root of negative 12 over 2, which is 6 plus or minus 2 root 3i over 2. So that's, now we're going to distribute this 2, and I'm going to get 3 plus or minus root 3i. So my alpha is 3, and my beta is root 3. So from this, I'm going to get 2 terms in the general solution, and I'll also get a term from the r equals negative 1. So I'm going to write down the general solution. Y equals, so for the root of negative 1, r equals negative 1, we have c1 e to the negative t. And then for these roots, the 3 plus or minus root 3i, I'm going to get 2 terms. I'm going to get c2 e to the 3t cos root 3t, and then c3 e to the 3t sine root 3t. So it's a third order DE, so my solution is going to have 3 constants, C1, C2, and C3. I'm getting 1 term from the real root and 2 from the complex root pair. Okay, so that's really the end of the lecture, but just stay a couple minutes more if you want to know where this strange cosine and sine is coming from in the complex case. So it comes from Euler's formula. Our solutions in general, if r is a root of the characteristic equation, a solution looks like y equals e to the rt. Now in the complex case, we've got e to the r, which is alpha plus or minus I beta t. That's e to the alpha t times e to the plus or minus I beta t. All right, and so let's just look at the case where we've got e to the alpha t times e to the I beta t. Let's look at the plus case. So it's this that we want to make sense of. The e to the alpha t you're seeing here. All right, but how is e to the I beta t turning into cos beta t plus sine beta t? So this is where Euler's formula comes in. This is e to the alpha t times cosine beta t plus I sine beta t. All right, and so let me just jump to the very last page where I have Euler's formula stated and a proof of it too. You don't have to know that, but in case you're curious, e to the I theta is cos theta plus I sine theta. All right. So once we're there, let's go back. Once we're there, this is e to the alpha. Oh, that looks like that's a t. E to the alpha t cosine beta t plus e to the alpha t I times I. So I'm going to put the I at the end. Sine beta t, and all this guy is times I. Then you have to use a fact that it's kind of beyond the scope of this course, but if you have a complex solution, both the real and the complex parts are solutions. So this is a solution and this is a solution. So I'm getting rid of the I and I'm plucking out the real parts and I'm writing those down as my solutions. So that's where the mysterious cosine beta t plus sine and sine beta t come from. They come from Euler's formula. And so they allow us to turn a complex root case into a real solution. All right, and that is the end of this section.